So congratulations, you are at the last section of the class. This is it. So let's go ahead and look at 10.8. We have complex numbers that we're going to be working with. So the definition of I, okay, square root of a negative number is defined over a set of numbers called the imaginary numbers. And the foundation of the set of imaginary numbers is the definition of the imaginary number I. So basically, that was just a glorious way of saying that I is equal to the square root of 1. The square root of negative 1. When you take the square root of a negative, it is equal to I. Also know that when you square I, so if you say I times I to get I squared, that is equal to negative 1. Okay? If you have the square root of a negative b, as long as b is greater than 0, as long as b is positive, then the square root of negative b is equal to I square roots of b. Okay, so examples: the square root of negative 49. The square root of 49 is 7, so the square root of negative 1 is I, so you get 7I. A good way of thinking about this is the square root of negative 49 is equal to the square root of negative 1 times 49, which is also equal to the square root of negative 1 times the square root of 49. And the square root of negative 1 is equal to I, and the square root of 49 is 7, so 7I is how we end up with that. Same thing with the square root of negative 8. I'm going to look at it as the square root of negative 1 times the square root of 8. The square root of negative 1 is I. The square root of 8, well, 8 is 2 times 2 times 2. So the 2 comes out front with the I, and 2 is left inside of the square root because we didn't repeat. And then over here, let's see, we have negative the square root of negative 12. Well, this is just like saying negative 1 times the square root of negative 1 times the square root of 12. Okay, the negative 1 came from right there. The square root of negative 1 came from right there, and here's the 12, okay? Anyway, this would be negative 1 times I, and the square root of 12 is 2 times 6, which is 2 times 3. So the 2 can come out. That will be negative 2I square roots of 3. So again, the negative came from this. The I came from the square root of negative 1, and then the 2 square roots of 3 was simplifying the square root of 12. So let's try some more. Square root of negative 121, that's like saying, and you don't have to, the answer is 11I. And you can just go straight there. But you could also, if you need to, break it down and say that's negative 1, square root of negative 1 times the square root of 121, and the square root of 121 is 11, the square root of negative 1 is I, and that's how we end up with 11I. The square root of negative 3. So that's like saying the square root of negative 1 times the square root of 3. Square root of negative 1 is I. There is no square root of 3. We have to leave it just like that. It doesn't simplify, so I square roots of 3 is our final answer. So this one is interesting to me because the square root of 3 doesn't simplify. Even though the square root of 3 doesn't simplify, you still have to bring that negative out of the radical, and it comes out, the negative 1 comes out as an I. So the first thing I'm going to do is call this I square roots of 32. And let's see if the 32 reduces. 32 is 2 times 16, and 16 is 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So 1, 2. So that's 2 times I, and the square root of 2, which gives us 4I square roots of 2. So on number 2, we got 3 parts, and we had the same question basically, though simplified in terms of I. So what we did here, the square root of negative 36 is I, and the square root of 36 is 6. So 6I and 2I for the square root of negative 4. Well, when you get 6I and 2I, and then you need to multiply those together, 6 times 2 is 12. But I times I is I squared, right? But you can't stop there. 12I squared is equal to negative 1. How do you know that? Well, we told you right here. We told you, so you should never forget it, right? I squared is equal to negative 1. So since we know that, we then had to say 12 times negative 1 is negative 12. So let's try that out. You want to pause the video and try this? I mean, you can. Or you could just keep watching me. I'll go ahead and call this I square roots of 4 times I square roots of 81. And I times I, well, I won't do that yet. The square root of 4 is 2. The square root of 81 is 9. So really, I don't like to say I2 and I9. Although that's perfectly correct, I think it looks better as 2I times 2 times 9I. Anyway, this ends up being 18I squared. And I squared, remember, I squared is equal to negative 1. So I just want to plug in a negative 1 for I squared. And our answer is negative 18. Okay, let's do another. This is I square roots of 81 over I square roots of 9, which is 9I over 3I. Okay, and right here, our i's cancel. And you're left with 9 divided by 3, which is just 3. Right here you have I square roots of 32 over I square roots of 2. Square root of 32, 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So 4I square roots of 2. How did I get 4? Because I brought a 2 out, I brought another 2 out. 2 times 2 is 4. 4I square roots of 2 all over I square roots of 2. Well, look what cancels. Look what cancels. Bam, 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 bam. And our answer is a nice 4. So let's look at some powers of I. I to the first power is equal to I squared is equal to negative 1. I cubed is equal to negative I, and I to the 4th is equal to positive 1. And then the pattern just keeps on going. You have I to the 5th, I to the 6th, 7th, 8th, and notice that it just keeps going I, negative 1, negative I, and 1. A lot of that is because, or I guess it is really because I to the 5th is the same thing as I times I to the 4th, right? Right? I mean, keep your base, add your exponents. And I to the 4th is equal to 1, isn't it? How do I know that? Well, it says it right there. And then the I stays the same, so I to the 5th is equal to I, and therefore you have this never-ending pattern, because I to the 6th is the same thing as saying I squared times, I don't know, I to the 4th. That's I to the 6th. Keep your base, add your exponents. And I squared is equal to negative 1. I to the 4th is equal to positive 1. And so that's how we get negative 1. Anyway, it's this never-ending pattern. So when we're looking at number 3, we want to simplify these high powers of I so that we can decompose the expression into multiples of 4 and rewrite the remaining factors as I or I squared or I cubed. So starting out on part A, basically I want to divide 476 by 4. And when you do, you get 119. So I could say this is I to the 4th raised to the power of 119. Why can I do that? Because 4 times 119 is 476. Okay? And now I know from the last page that I to the 4th is equal to 1. So I could replace the I to the 4th with a 1 to the power of 119. And 1 to the power of 119 is equal to 1. So I to the 476th power is equal to 1. Now, what I want to do here, you can say 65 divided by 4 if you want, but you get a decimal, okay? So go one below it. Go 64 divided by 4. Okay, 64 divided by 4 is 16. So I could call I to the 65th. I could call that I to the 4th to the 16th. Why? Because 4 times 16 is 64. And then I could multiply by I again. And this would be, and again, this would be I to the 64th and I, which is I to the 65th. Now, I'm not going to rewrite it like that because I'm still trying to find out what I to the 65th is equal to. Anyway, I to the 4th is equal to 1. So I'm going to replace I to the 4th with 1, and I'm going to call this to the 16th power. And I is just equal to I. So 1 to the 16th is 1. I is I. Our answer is I. Let's try another. Does 4 go into 95? No, it does not. Does 4 go into 94? 94 divided by 4 is... No, it's not. Does 4 go into 93? No, it doesn't. Does 4 go into 92? Yes, it does, 23 times. So I could rewrite I to the 95th as I to the 4th to the 23rd power. Because, I mean, the directions say rewrite the expression as multiples of I to the 4th. And that's what I'm doing. I wrote I to the 65th as I to the 4th to the 16th power, and then I had to multiply it by, because 4 times 16 is 64, I had to multiply it by another I to get I to the 65th. And then I didn't have to multiply I to the 4th to the 119th by another I or anything like that, because 4 times 119 is 476. But I to the 4th to the 23rd power is I to the 92nd. But I needed to be I to the 95th. So I need to multiply I to the 92nd by I cubed. And again, I'm not writing it as I to the 92nd. I'm writing it as I to the 4th to the 23rd. So I to the 4th is equal to 1. So 1 to the 23rd times I cubed. I cubed is equal to negative I. 1 to the 23rd is 1. And so our answer here is negative I. Moving right along, let's talk about, identifying what is the real part and imaginary part of a complex number. A complex number is in the form of A plus BI. Okay, so we have a real part and an imaginary part. Looks like a binomial, okay? So the real part in part A is 3. The imaginary part is 4, right? Because the I had a 4 with it, so that was the imaginary part. and the other part that didn't have I was 3. On part B, 47 is the imaginary part, and there was no real part, right? So we'll just say 0. There was 0 of them. On part C, the imaginary part, and it may be easiest to identify that imaginary part first. So the imaginary part is the -2, and everything else is the real part. And on part D, the imaginary part is, I don't see an I anywhere, so there's 0 of them, and the real part is -8. And on part E, the imaginary part is 5/6. The real part is everything else, or excuse me, -5/6. The real part is everything else, so 3/4. So now let's talk about the addition, subtraction, and multiplication of the of complex numbers in that order. Okay, so we're going to start with addition. We got 5 part A and B, and part F. E and F look like they are addition. So basically what you do, if you have a 3 minus 2i plus a 4 plus 7i, you combine your like terms. You say, and especially since it's plus, you just say 3 plus 4 is 7, and -2 plus 7 is 5i. Okay, now if this was a minus sign right here, I would need to rewrite the binomial in the back as a -4 and -7i if it was a minus sign. But since it's plus, you just pretend that it doesn't have parentheses. Okay. So in this case, on part A, the 4 and the 1 is the real part of the problem. The imaginary part is the -9 and the 1i. So 4 plus 1 is 5. And I got that, so that's saying 4 plus 1. Okay, and that was from this. And -9 plus 1i, -9i plus 1i is -8i. And what I was saying is -9 plus 1, and we had a I, and so the -9 came from right here, and the 1 came from right there. That's confusing, in the way it's crisscrossed. Okay, on the first part, there's no real part. It's only imaginary, and that's the -4. We're going to combine that with the 5. So -4 plus 5 is just 1i, and then plus a -1. And we're done with that one. Part C, this is our first subtraction one. I'm just going to rewrite it to clear the parentheses. The first group didn't need parentheses, but this second group right here, I need to distribute a -1 to it. -1 as in what's in front of that binomial, what's in front of that that complex number right there is a minus sign, so distribute a -1. So -1 times 1 is -1. -1 times 2 is -2i. So I can say my like terms, 14 minus 1, I can say that is 13, and then -8i and -2i is -10i. So just the same way you would be working 14 minus 8x minus 1 plus 2x. The same way you would simplify that expression. The answer to this would be 13 minus 10x. We're just dealing with i's, with imaginary numbers instead of x's. Okay, we have another subtraction problem. I kind of like what I did last time in rewriting the problem. Now this first complex number doesn't need to be rewritten to take the parentheses off, but this one, I need to distribute a -1, so that will be minus 1/14 minus I. And so I'll say my like terms, I can combine 4/7 and -1/14, and then I can combine -9i and -I. So that will be negative 10I and then 4 over 7 minus 1 over 14. If you type that in your calculator, you get 1/2. If you're going to do 4 over 7 by minus 1 over 14 by hand, you need to find a common denominator. Right here, negative 19I plus I, they're like terms. So just negative 19 plus 1, that's negative 18I. And as I'm writing this, I'm thinking I've been writing these answers the way I like, the format that I like. But I guess it wants you to put this in A plus BI form now that I go back and read the directions. So if I'm going to put this in A plus BI form, there is no real part to this. There was no real part in the original. So it would be more correct to call this 0 minus 18I if you were going to put this in A plus BI form, this being your A, the negative 18 being your B. Let me go back and see if any of the others need to be rewritten. This is in A plus BI form. This is not. You would want to call that negative 1 plus I. Basically, put your I's in the back. This one's in A plus BI form. This one was not. I guess it'd be better to write 1/2 minus 10I, putting your I's in the back. And that's A plus BI form. Let's do the last one. So for this one, it's addition. So we don't really need to rewrite anything. The parentheses really aren't even needed in this case. So you have a negative 2/3 and a 1/3 that are like terms. So if you add negative 2/3 together and positive 1/3 in the calculator or by hand, you get negative 1/3. And then I'm going to combine negative 1/2 I and positive 1/2 I. They completely cancel to give you 0 I guess. Now, I personally like the answer like this, but I guess this is more correct. So now let's look at multiplication. Multiplication, notice you got 3 minus 2I times 4 plus 7I. This dot, it tells me that I'm looking to do the multiplication. It does not have to have a dot in between it though. They could have just said 3 minus 2I, open another set, 4 plus 7I. When they butt them up together like that and you don't see a little dot there, or you don't see a plus sign, or you don't see a minus sign, and you're like, what do you do? Well, if there's nothing there, you multiply. So I'm just telling you, they don't have to put that dot there if they didn't want to tell you that it's multiplication. Anyway, this is I guess a real detailed way of looking at distribution, at foiling out. Sometimes all those details can get confusing, so this is the way I do it. I say 1 times front times front. 1 times 5 is 5. Now I say 1 times 6I. That's the outer. So 1 times 6I is 6I. Now the inner, negative 2 times negative 2I times 5 is negative 10I. And now the lasts, negative 2I times 6I would be negative 12I squared. So let's make this look better. 5, and then we have like terms with the 6I and the negative 10I. So that's negative 4I. And then I squared is equal to negative 1. So now I can call this 5 minus 4I plus 12. And 5 plus 12 is 17 minus 4I. Now, when I was showing you the first full, I did kind of repeat the outer, the inner last. All I do is I say -1 times -1, -1 times 10. I exhaust this -1. I give it to everybody. And then once I've multiplied that -1 by everything, I then multiply the -2i by everything in that second complex number. So -1 times -1 is +1. -1 times 10i is -10i. So I've given -1 to everything. Now -2i times -1 is +2i. And -2i times +10 is -20i squared. Okay, -10 and +2 give me -8i. And then -20 times -1, because I squared is equal to -1. That's like saying +20. So our answer is 21 minus 8i. Okay, right here we have 3 times 3 to get 9. 3 times -2 to get -6i. -2 times 3 to get -6i. And -2 times -2, -2i times -2i is +4i squared. This gives me 9 minus 12i plus 4 times -1. So that's -4 and a +9. So 5 minus 12i. This is the last one. Okay? So we have, and this is a difference of squares formula, really, because it's a plus b. Well, let me rewrite that. Let me call it a minus b, because that's what we're given is minus. A minus b and a plus b. If you're given that, all you got to do is say square your a, square your b, and put a subtraction sign in between it. So let's do that with this. Let's square the 1/2. And let's square the 3i. And we get 1/4 minus 9i squared, because you got to square the 3i. And let's see, I squared is equal to -1. So 1/4 minus -9 is like saying 1/4 plus 9. And you can do that in your calculator, or to do it by hand, we're going to get a common denominator, which would be 4. To make 9 have a denominator of 4, multiply it by 4/4, which is 36 over 4. So keep your denominator, add your numerators, 37 over 4. And there's not, our I squared was -1. So there's really not an imaginary part of this left.